Hey everyone, and welcome. Today we're going to pull back the curtain on artificial intelligence. We're going to look at 3 totally different ways that machines can think. It's kind of like they have these distinct personalities or minds that they can use to solve problems, make predictions, and figure out the world. All right, let's get into it. So, you ever stop and wonder about that? It feels like this huge, complex question, right? We hear about AI constantly, but what is actually going on under the hood when a machine has to make a call? Well, that's exactly what we're going to unpack right here. So here's the plan. We're going to start with a model that basically relies on the wisdom of crowds. Then we'll jump to another that's all about finding the perfect dividing line. After that, we'll see how a machine can update its own beliefs when it gets new information. And finally, we'll put them all side by side so you know which tool is right for which job. All right, first up, let's talk about teamwork. Our first algorithm, which is called a random forest, isn't about one single genius making a decision. No, it's all about harnessing the collective intelligence of a huge group. So what in the world is a random forest? Well, imagine instead of trusting one expert, you get a whole committee of them together. Each expert is just a simple little decision tree. The algorithm creates a whole forest of these trees, and they all get to vote on the final answer. It's a pretty amazing idea, really, that combining a ton of simple viewpoints can lead to a really smart outcome. The best way to think about it is like diversifying a financial portfolio. You know, you don't put all your money into one single stock, right? Because if that one tanks, you're in big trouble. A random forest does the exact same thing with its predictions. Any one tree in the forest might be a little off, but when you average them all out, those mistakes tend to cancel each other out, and you're left with a much more stable and accurate final call. The process itself is actually pretty straightforward. First, the algorithm builds a whole bunch of different, unique decision trees. Then you give it a problem, and each tree in the forest gets to cast its vote for what it thinks the answer is. And the final prediction? Well, it's just the one that got the most votes. It's literally democracy in action, but for data. And you know what the best part is? Even though we're talking about this massive forest of decision makers, actually putting this thing to work is incredibly easy. I mean, with a tool like scikit-learn, it literally just takes a couple lines of code to summon the wisdom of an entire forest. It's that simple. Okay, let's shift gears and look at our second machine, mind. If random forests are all about consensus and popular vote, support vector machines, or SVMs, are all about precision. They're not trying to find what's popular. They're looking for the single, most perfect dividing line. So the key thing to get here is that an SVM kind of thinks in shapes, geometrically. It looks at all of your data points scattered around, and its one and only goal is to draw the absolute cleanest boundary possible between the different categories. That boundary is called a hyperplane, which, is really just a fancy word for a line that can exist in more than 2 dimensions. The whole goal of the SVM is to find the line that creates the biggest possible gap between the groups.
In this approach, it's a total workhorse out in the real world. SVMs are used for all sorts of things, like text classification, figuring out if an email is spam or not, analyzing sentiment in product reviews, recognizing images, and even reading handwritten zip codes to sort mail.
But like any tool, it has its pros and cons. The huge advantage is its high accuracy, especially when your data is pretty clean and the groups are easy to tell apart. Think of an SVM like a bouncer at a fancy club with a very clear VIP list. It's fantastic at separating those 2 groups. But it's not so great at a huge, messy music festival where the lines between who's who are kind of blurry. That's where it can struggle with really large, noisy datasets.
And hey, sound familiar? Don't let the fancy name fool you. Just like with random forests, actually using a powerful SVM classifier is as simple as importing the right tool and putting it to work with a single line of code. All that complexity is tucked away, leaving you with all the power. All right, our third and final model takes a completely different path. This one's a whole different ballgame. It's not about voting, it's not about drawing lines, it's about something that's actually very human. Updating what you believe when you get new information. Welcome to the world of Bayesian inference. At its heart, Bayesian inference is a way for a machine to logically, to change its mind. It starts with an initial belief about something. That's called its prior probability. Then, as it sees new data, new evidence, it uses that evidence to update its belief. The result is a new, more informed belief called a posterior probability. It's a formal mathematical way to learn from experience. And this is the famous equation that makes it all happen. Now, I know equations can look scary, but stick with me, because this one is actually pretty intuitive when you break it down. We start with P of H, the prior. That's just our initial gut feeling about something, before we've seen any real evidence. Then there's P of D given H, the likelihood. That's the chance of seeing our new data if our initial gut feeling was right. And when you combine your prior belief with the likelihood of the new evidence, you get P of H given D, the posterior, your new, updated belief. See? It's a really elegant way to connect what you see to what you think is true.
So the ultimate goal here is to find what's called the maximum a posteriori, or MAP, hypothesis. In plain English, after looking at all the evidence, the machine is just asking, okay, what is the single most likely explanation for everything I'm seeing right now? And this is where the real magic is. It lets us do something that's actually kind of hard for our own brains to do sometimes. It lets us flip the logic around. For example, if we know the probability of having certain symptoms if you have a disease, Bayes' theorem lets us figure out the reverse, the probability you have the disease given that you have those symptoms. It is an incredibly powerful way to reason about the world. So we've looked at 3 totally different ways a machine can think. One uses consensus, one uses precision boundaries, and one updates its beliefs. The big question is, how do you know which mind is the right one for your problem? This pretty much lays it all out for you. The random forest is your go-to general-purpose workhorse. It's great for stable, reliable predictions. The SVM, on the other hand, really shines when you need super high accuracy and you have a clear separation in your data. And Bayesian inference, that's what you want when you're dealing with uncertainty, and you need your model to learn and adapt as new evidence rolls in. The main takeaway here is there is no single best model. It's all about choosing the right tool for the job. And that leaves us with one last thing to chew on. We've explored the democratic mind of the crowd, the precise mind of the line drawer, and the adaptive mind of the learner. Each has its own way of seeing the world, its own strengths, its own blind spots. So as you think about AI out there in the world, which way of thinking gives you the most confidence? Which mind would you trust most with an important decision? It's a fascinating question to consider. Thanks for joining me on this one. So where's this from? It's all coming from the channel Learn with Praveen.